Good afternoon, everybody. Let's get started. For announcements, check the Canvas page for upcoming assignments. There's a pre-lab, a quiz, and a homework coming up. That's all posted on Canvas. Uh, so Lab 1 is due this Friday, so check that due time. Generally, the labs are due 1 week after you perform them. Pre-lab 2 is due this Thursday. Both of those are one per team. So going forward, labs and pre-labs, those reports or those submissions are one per team. My office hours are right after class. If you'd like to stick around after class and stay up on this session to talk about anything. So let's continue on with the material, and we're going to finish up what I consider to be the review material, the material you might have seen before, and I think we're going to get into some new topics that you haven't seen before. So let's move on to that. I'd like to go back to talking a little bit about voltage division, or kind of a little review from last lecture, talking about voltage division, because we're going to talk about potentiometers and voltage division will be used there. But voltage division is used when you know the voltage across three series resistors or more series resistors. You just have a set of series resistors, in this case three, and you want to figure out what is the voltage across one of those resistors. So we talked about this pattern that shows up. We derived this equation. For example, if you want to know the voltage across resistor R1, which I've defined as V1, and let's say you know the voltage Vs across the series set, then the voltage across R1 is Vs, voltage across the series set, times this ratio. On top goes the resistance across which you want to find the voltage, and in the denominator on the bottom is the sum of the resistances in that series set. We also talked about current division, and there was a pattern that showed up here. If you want to know the current through each resistor of a parallel set, when you know the current coming into that parallel set, for example, IS is coming in and want to know I1, I2, or I3, we talked about how to do that. Okay, so these situations of series and parallel resistors show up often, so it's worth knowing voltage division and current division. So going back to voltage division and applying that, uh, let's talk about potentiometers. So potentiometers are three-terminal devices, and you could think of them as an adjustable resistance, or actually two adjustable resistors, as you will see. These are often used in, let's say, some kind of human interface, like a volume control or the adjustment of a voltage. Like, it's basically if you turn a knob on something uh, to adjust the volume or some other parameter, you might be turning the shaft of a potentiometer. Okay, so this is what a potentiometer would look like, several different types here. So the potentiometer in your kit looks like this. This is mountable on a circuit board or a breadboard. Here's the kind of the top or diagonal view of the potentiometer. Here's the bottom view. It's a three-terminal device, right? You can see the three terminals there. Here's another multi-turn potentiometer right there. You can see that. Here's a potentiometer where you turn the shaft of the potentiometer with a screwdriver, small screwdriver. You'd see the three terminals. This is a potentiometer. You can see the shaft. You can see it's knurled, so you put a knob on it. This might be through a panel, so you can put a knob on the outside and control the resistance, which we'll take a look at, and the three terminals here. The schematic symbol for a potentiometer is this. It looks like a resistor with two terminals, but you have this third terminal with an arrow. It's often drawn like this. And so these are the three terminals, and you're given one resistance value, okay? This RP value might be 10K ohms, 1K ohm, 5K ohms, something like that. That's the schematic symbol. If we look at a cartoon of how a potentiometer is constructed, it would look like this. Okay, so here are the these three terminals at the bottom, and let's just look at terminal A and terminal B. These lines at the bottom are conductors. Assume those are metal, and then this arc here is resistive material. So there's an arc of uniformly distributed resistive material, often uniformly distributed, but and what that resistive material does is it gives you a resistance per unit length. So for example, between A and B here, between the ends of this arc, you might have 10 kiloohms, 10 k ohms. And if you could shorten that material to half of its length, you would have 5 k ohms. If you had a tenth of its length, you would have 1 k ohm. Okay, so the resistance along that arc is proportional to the length along that arc. Okay, so that resistive material is between A and B. This terminal in the center labeled W is called the wiper. Okay, that wiper wipes along or drags along the resistive material. So you can imagine this is metal here, and then somehow it rubs along this, right, this ring here, and then there's a metal terminal or metal kind of, well, wiper that connects W to some point along this resistive material. And there would be a screw or a knob that would let you turn this wiper to position it from all the way to the left, right, to A, or any position along this resistive material, or all the way to the right, where you directly connect to B. Okay, so the resistance in this case between A and W is determined by the length of the resistive material between A, terminal A, and the wiper position. The resistance between B and W is determined by, well, the length along the resistive material between B and where the wiper contacts. Okay, so someone says, so it's almost in the chat, almost similar to a valve for a water source. It's sort of like a valve, but it has three pipe connections to it. So I got to think about maybe a practical example, but you'd have to have three connections. So there might be some practical example I can think of. Let me think about that, how to get a fluid flow analogy out of this. We dig in a little deeper here. Let's put the schematic symbol and cartoon of the potentiometer here. So I have a value defined here. I have a value of 10 k ohms. So that 10 k ohms is the length, or it's the entire length. It's the resistance of the entire length along the arc between A and B. So if you didn't connect anything to any of these terminals, and then you connect an ohm meter to measure resistance between A and B, but leave W disconnected, you would measure 10 k ohms, 10 kiloohms from A to B. That's what that 10 k ohm means. Now, so you can see that there are really two sections of resistive material here between A and W and WB and B. So you can break this equivalently, break up the schematic symbol and represent it with two resistors, a resistance between A and W and a resistance between B and W. Okay. So let's do that. Let me represent that potentiometer like this. So between A and W, I have R1. That would be the resistance here along this smaller portion of the arc. Resistance R2 would be the resistance between B and W, the resistance along the longer part of the arc as shown here. And remember, you can reposition the wiper so you can make those arcs any length, but they have to sum, that distance has to sum to the total arc length between A and B. Okay, so, but note that total arc length between A and B is defined here as 10 k ohms, and R1 plus R2, right, the little arc plus the big arc has to equal the whole arc, so RP is R1 plus R2. Now, to be able to write an equation to define what the resistors, what those values are, R1 and R2, let's define T as the fraction of the full turn range. Okay, so in other words, right here, if I turn the wiper all the way to the left, I would call that, in this case, in this diagram, T equals 0. In the position it's in, that's about 1/3 of the way from A to B, so I might call that T equals 1/3. If I have the wiper at 1/2 of the position between A and B, that would be 1/2. And if I turn the wiper all the way to the right, that would be T equals 1. Now, you don't take this as all the way to the left is always T equals 0 and all the way to the right is always T equals 1. You could define it as all the way to the right is T equals 0 and all the way to the left is T equals 1. It depends on how the potentiometer is laid out physically and how the terminals are connected. But this lets you assign a parameter that represents the fraction of the turn from nothing to full scale on this potentiometer. Okay. And someone says, okay, can there be, in the chat, can there be multiple W's and I'll say multiple wipers or multiple wiper terminals in a potentiometer, or just one? Typically in a potentiometer, there's just one wiper. There's just one connection between W and some position on that resistive material. You can imagine, I'm sure there's some specialized, what they would call ganged potentiometers, like you can have ganged switches, which might stack these up and you might have multiple potentiometers operating off of one shaft. But typically what you're going to see is just one wiper there. Okay. So, so what we can do is we can figure out, well, what is the value of R1 and R2 based on RP and the position? And so here's what it would be. In the way I have it defined down here, T defined down here in the lower left, RP or R1 would be RP times T, right? And R2 would be RP times 1 minus T, right? If you add those together, you would get RP, okay? And so we can create a table. And just for an example, let's say we create this table. What's the position T, 0 to 1? What is R1? What is R2? Well, if I make T equal to 0, that means the wiper is all the way here on the left, and the metal of the wiper is connected right next to or on the metal of terminal A. That means there's 0 ohms between A and W, because metal touching metal or close to it. And that would be 0 ohms. And the remainder of the resistive material is between B and the wiper if it's at T equals 0. Okay, so that would be T equals 0. If I turn to the 1/3 position, sort of like it's drawn here, then 1/3 of that material, 1/3 of 10K would be between A and W. I have 3.3 K ohms. The remainder of that material between B and W, 6.7 K ohms. Okay. And likewise, if I move the wiper to halfway, I'd have half the resistive material between W and A and half between W and B. And if I turn the wiper all the way to the right, the wiper would be touching or almost touching B. So I'd have 0 resistance between W and B because I have metal touching metal there. And 10K would be between A and W. Okay, so you can imagine this. You can imagine how, as you turn like to infinite positions, it's continuous. You can turn to any position in there. You can make R1 anything you want, but R1 plus R2 is RP, and so you have this infinitely adjustable resistor. Okay, so someone asks, is this how dimmable lights work? In general, no, and we can talk about that later when we talk about pulse width modulation for dimmable LEDs when you're using a DC power source, and we can talk about dimmer switches as well. We talk about AC a little bit. So I'll leave that till later, but a potentiometer could be used as the input from a human to give a signal to something that's controlling pulse width modulation or other approaches. but you wouldn't use this as like a resistor in series with a light bulb because it would be very power inefficient. Okay. Okay, so someone asks, how does the electricity flow? How does current flow through the potentiometer for the position of the wiper to change the resistance? Well, so forget about the potentiometer here. Look at the equivalent circuit up here. So you can imagine you can attach these two resistors with these connections into a circuit any way you would like. So you could have voltages applied across these terminals. You could have this connected into other resistors. So just by looking at this, you can't tell which way current is flowing, okay, because you don't know the voltage. I could connect voltage sources to these two resistors to make current flow either way through either of these resistors. Okay, so you can't tell. But I'll show you an example circuit that is common that turns this into a voltage divider to create a reference voltage. So I'm going to show you that. And then there's either a homework problem or a quiz problem that where you will see an example of a potentiometer just used as a variable resistor. Sometimes variable resistors are useful because when we get to op amps, operational amplifiers, you're going to see that changing a resistor value can change the gain of an amplifier circuit. Okay, so you might want to have an adjustable gain, and that's where the potentiometer as a variable resistor would come in. But let's keep it kind of straightforward, baby steps first. Let's talk about an adjustable voltage that you can create with a potentiometer. Okay, we're going to use the potentiometer as a voltage divider. And so let's assume this circuit here. Let's say I want a variable voltage V out. So I turn the knob and I want a voltage between 0 volts and 12 volts. In this circuit, this circuit will do that. Now, I'm also assuming I'm not connecting anything to the right of these two terminals where I've specified V out. Because as soon as I connect something, if I connect another resistor there, then it's not just a voltage divider created between these two equivalent resistors of the potentiometer. I have to take into account what I connect to the output. But if you assume that that output is connected, let's say, to a really big resistor, like 1 megohm, or I'm connected to the input of a device like an operational amplifier that has equivalently a big resistance at its input, then this circuit works very well to provide an adjustable voltage reference. That's application information, but let's just assume right now you have this circuit, you take a voltmeter and you're going to measure this output voltage, and you just want to figure out, well, how does this circuit create a variable voltage? I can view it on my voltmeter. Almost no current flows through a voltmeter. So we're gonna assume no voltage, or not no voltage, no current flows out of these or into these terminals. But let's see how this works. So what I'm going to do is I'm going to take this circuit and I'm going to replace the potentiometer with the equivalent two resistors, right, R1 and R2. R1 plus R2 equals RP, 10K. And let's see how can this be? How does this potentiometer create this variable output voltage? Okay, this is a voltage divider. The output voltage is the voltage across resistor R2. Okay, I have series resistors, and I'm looking for the voltage across one of those resistors so we can use the voltage divider relationship. The total voltage across this series pair of resistors is 12 volts, or Vs. So using voltage division, V out, the voltage across R2, is Vs, the voltage across both resistors in series, times this fraction. On top goes the resistance across which you want to find the voltage. In the denominator is the sum of the series resistances. Okay, so just the potentiometer itself is used to create this voltage divider. So let's look at the range of R1 and R2 and figure out, well, what is the range of that output voltage? Okay, so as we saw on the previous slide, both R1 and R2 range from 0 to RP. Now there's a relationship between R1 and R2, but each one of those individually can range from 0 to RP, 0 to 10K in this case. And R1 plus R2 must equal RP. So in the bottom here, the denominator of this fraction, that's just RP. That's always 10K ohms. So no matter where you turn the knob of this potentiometer, the denominator's a constant. It's 10K ohms. R2 changes, right? R2 changes from 0 to RP, right? So you have this fraction that ranges from 0 over 10K to 10K over 10K. So that fraction ranges 0 to 1. So you have this fraction ranging from 0 to 1 as you turn the knob. Multiply that by Vs. That means V out goes from 0 to 12 volts. So as you turn the potentiometer knob over the full range, V out ranges from 0 volts to 12 volts, or Vs here. So this is a way to create a variable voltage. But again, you're going to see this in a homework problem. Once you connect a resistor here, if that resistor is on the order approximately, in the range of within an order of magnitude of R2 or R1, that messes up the voltage divider, because then you've put a resistor, a load resistor, we're going to call it, in parallel with R2, and you have to take that into account in your voltage division equation. Okay, but let's leave that aside for now. If you're just trying to create a reference voltage, let's say for a thermostat, we're going to do that. You can use the circuit and turn the knob and get any voltage out between 0 and 12 volts. For your lab, you're going to do this. You're going to create a variable voltage. But for lab, I don't want you to create a voltage that ranges from 0 to 12. I want the voltage to be restricted within a certain range. So we'll talk about this, but you're going to add a resistor. Let me draw this, or let me point this out over here on the left. You're going to put a resistor up above the potentiometer and a separate resistor below the potentiometer. So this circuit will have 4 resistors in it. Okay. I'm going to try to get to a pre-lab 2 preview today. We'll talk about that. Okay. Okay, so someone asks, this is a good question. Is the current also affected by the potentiometer? Let's suppose that you don't have anything connected to the output here. As I turn that potentiometer's knob, R1 and R2 still equal 10K ohms. So you're going to have 12 volts divided by 10K ohms flowing out of the source, down through R1, down through R2, and up into the source. So, if this is 10K, 12 volts divided by 10K is like 1.2 milliamps, if I did that right in my head. So no matter what the position is of the potentiometer, you're still going to have 1.2 milliamps flowing down through these 2 resistors. Again, assuming you don't connect anything to the output other than a voltmeter. So current is not affected in the circuit as you turn the knob. All right, so let's talk about, let's go back to Ohm's law. Let's work an Ohm's law example. So give this a shot. We talked about Ohm's law last time. Let me start the clicker machine here. So you have a circuit element A, could be a source, could be a sub-circuit, who knows? It's connected to a resistor. Let's say you know that you have IA equal to 4 amps with this reference direction, and you have a 12 ohm resistor connected to A. The reference polarity for Vy, this voltage across the resistor, is given to you. What is Vy? Give that a shot. All right, so we have current IA defined. 4 amps left to right through circuit element A. So 4 amps comes up and into the left side, or from right to left through the 12 ohm resistor, as defined by this reference direction at the bottom. Well, I've pointed the reference direction of IA into the negative side of VY, and that's not what we want for Ohm's law. For Ohm's law, you need the reference direction, the arrow, pointed into the positive reference polarity of the variable or the voltage across the resistor. So I could do one of two things. Instead, I have IA coming in from the right. I could flip the polarity of VY and then call it negative VY. Okay. Or I can flip the direction of the current, the reference direction of the current, and call it negative IA or negative 4. And that's what I chose to do here. I chose to say, well, I have 4 amps going right to left, so I have negative 4 amps going left to right. That puts my reference direction into the positive side. So now I'm working with negative 4, 12, and VY for my variables in Ohm's law. So V equals IR, negative 4 times 12, you get negative 48. Okay. All right. And if you'd like to work more of these Ohm's law examples, just stop by office hours. I can just create some with reference directions pointing either way into the reference polarity with positive and negative currents and voltages. So if you want to work on that. All right. So we've covered voltage division, current division, Ohm's law. I think much of this was review, maybe except for potentiometers. That's an application of voltage division mostly. We're going to move into some material now, which you might not have seen. But first, let's see, let me do this. What I'd like to do is actually give you a preview of Lab 2 relating to the material we just talked about. So let me bring a preview up here. Okay. So Lab 2 is about resistive circuit analysis. You're going to be building a circuit on a breadboard with resistors and then connecting those resistors to a power supply. So in one of the problems, one part of the lab, you're going to do this. You're going to build a series set of resistances, connect those resistances to a power supply, right, that mimics or that represents this independent voltage source. And what you're going to do is you're going to demonstrate Kirchhoff's law, and you're going to demonstrate voltage division. And so you're going to use theoretically these values to calculate what are the voltages across each of those resistors in using voltage division, and you're going to show that the sum of the voltages around a loop equals 0. So you get to see, it's kind of satisfying to see KVL work, to prove to yourself that it works, and then as you go into future circuits, you'll see that you can trust KVL in the lab, and you'll be able to practice using the voltmeter, the multimeter set on voltage, and how to orient the positive and negative terminals to make sure you're getting the reference polarities right. You're also going to look at a parallel resistor circuit. I've got one series resistor here, but R1 through R3 are these parallel resistors, and you're going to exercise Kirchhoff's current law and also practice current division and make measurements of the values so you can prove KVL or KCL. And then you're going to design and build a variable voltage source. So here is that circuit that looks a lot like that last slide we talked about with the potentiometer. This circuit, though, has the potentiometer and 2 extra resistors on the top and the bottom of the potentiometer in the circuit. And so you want V out to be a variable voltage, and you have some requirements here. So you want this output voltage to change according to the spec table, as you turn the potentiometer potentiometer knob. And you want the minimum output voltage to be 1 volt and the maximum to be 2 volts. So when you turn all the way to the extreme to the left, you measure 1 volt with a voltmeter at V out. You turn all the way to the right, you get 2 volts, and you have this 5-volt source. So if you didn't have RA and RB, the output would be 0 to 5 volts, but you want to limit that, have some limited range. So you're going to have to figure that out. And so you'll work on that. I'll point out that you have this requirement for 8 milliamps maximum current. Don't worry too much about that, because if you have 5 volts across a 10K ohm resistor, unless you build the wrong circuit, there's no way to exceed 5 volts divided by 10K for this circuit, which is less than, it's actually half a milliamp. So this is just, you want to make sure you're less than 10 milliamps, even if you built the 8 milliamps, even if you built the circuit wrong. So because the resistors could get hot and you'll burn out the resistors. Okay, so you're going to be building that. Here's that circuit again. Don't forget to represent that potentiometer like this. Represent it with two separate resistors. Okay, so you actually have 4 resistors in this voltage divider circuit. You have RA, RB, and then between those R1 and R2. Okay, and you know that when you turn the potentiometer all the way to the left, you're going to get one of these resistors 0. One of these resistors will be 10K. When you turn the potentiometer all the way the other direction, then those values swap. The other one is 0. The other one is 10K. And from that, you can get 2 equations, 2 unknowns to figure out RA and RB. RA and RB are the unknowns here to get that range of 1 volt to 2 volts. All right, so you'll be working on that for the pre-lab and for the lab this week. And it's a practical circuit. This is a practical circuit to create a reference voltage, maybe an adjustable reference voltage for a comparator using an op amp. We'll talk about that, like for a thermostat. Okay. All right, so now let's move on to the new material, as I've been promising. Okay, looks like it's up now. We're going to talk next about an analysis technique called node voltage analysis. Node voltage analysis is an approach to solving certain circuits that have resistances and often voltage sources or some current sources, voltage sources and current sources, in a way that's methodical. In other words, for complicated circuits, you could write, if you're trying to solve for voltages throughout the circuit, you could write several KVL equations and KCL equations, and hopefully you have enough independent equations to solve for the number of unknowns that you have. Node voltage analysis is a way to methodically write equations and get an answer for voltages throughout the circuit, and then you can solve for currents and powers throughout typically a resistive circuit. Okay, so to talk about node voltage analysis, we need to first define node voltages, and then we'll move on to the analysis part. So, node voltages. Node voltages are defined like this. A node voltage is the voltage between a node and a reference node. That doesn't clear things up, does it? So you have a voltage, which means you have to have 2 places in a circuit to measure or define a voltage. And so we're going to have a node where we define a node voltage, and then a reference node where against which all of the node voltages are referenced. The reference node is the negative side of the polarity for every node voltage defined in a circuit. And we often have a more familiar term, I'm sure you've heard, uh, that is a synonym for reference node, we're going to call that ground. Okay. Let me show this using an example circuit. So I have this circuit. I have resistors. I have a current source. And so for me to define node voltages, I have to define, or I need defined for me, a reference node. One of these nodes in this circuit is going to be a reference node, ground. And so typically reference node symbols are these. These are ground symbols, often called ground symbols. Okay. I am going to choose this one symbol to use often. And what that symbol does is it defines the node to which it is attached as the reference node. Okay, so remember, a node is the entire connection among circuit elements. So that means this whole connection here, it's not just one junction point, it's the whole node. That whole node is the reference node because I've drawn this ground symbol, this reference node symbol connected to this node. I happen to choose the bottom of the circuit. It doesn't have to be the bottom of the circuit, but that's just where I chose it here. Okay. All right. So let's define a node voltage. I'm going to put this V1, this is a node voltage next to this upper left node here. So that V1 applies to this entire node, this pinkish purplish node here. Notice that V1 does not have a polarity. I have not explicitly put a plus and a minus to show where's the positive side of V1 and where's the negative side of V1. You need 2 points in a circuit to define a voltage, and you need to have a polarity for a voltage. I have not shown that here. With node voltages, with a node voltage, the polarity is implied when you have a ground node defined, a reference node defined, right? The reference node is the negative side of the polarity. So this is the negative side down here. The node voltage is where the positive sign goes for the reference polarity. So V1 is the voltage, if I were to draw it out, the voltage between this upper left node and the bottom node. Okay. If I define a voltage V2, node voltage V2, I can write that voltage here, right next to this node. Just put it close to a node, it implies to the whole node. And that's going to be the node voltage of this brownish node here. It's the entire connection between those resistors. The positive sign for V2 goes, well, right next to that node. The negative sign goes at the ground node, at the reference node. So like that, okay? So I'm actually, when I define a ground node, I can write a node voltage. I can define a variable next to a node, and I don't have to write polarities because they are already defined. Negative is at the reference node. Positive is at the node next to which the variable is written. So here's V3. Right? V3 is this darker purple node with the positive at that upper right node and the negative at the blue node. Now the negative sign of V3 is at the lower, is at the bottom here. The positive is at the top at that purple node. That doesn't mean that V3 is a positive value. V3 can be positive, it can be negative, it can be zero. So just because I have a positive and negative written as such, it doesn't mean V3 is a positive value. V3 can and often will be negative. Node voltages can and will be negative. Okay, so think of it this way. Think of node voltages this way. If you were to use a voltmeter, the reference node is where you connect the negative lead, the black lead of the voltmeter. Okay, and the non-reference node of the node voltage is where you connect the red lead, the positive lead of the voltmeter. And then the node voltage is the voltage between those two nodes. So if I want to measure V1, forget about these polarities that I've drawn. They're redundant here because I have a ground node defined. If I want to measure V1, I put the red lead at V1, I put the black lead at ground. If I want to measure V2, I put the red lead at V2, I put the black lead at ground. If I want to measure V3, red lead goes on the V3 node, black lead goes on the reference node, the ground node. Okay. So that's the definition of node voltage. I haven't talked about node voltage analysis, but this is a prerequisite for doing that analysis. Now I want to make a comment about the location of the reference node and even changing the location of the reference node. So we just worked with this circuit. I have V1, V2, V3 defined. I have a reference node defined that defines the polarities for V1, V2, V3. Let's take that same circuit and let's suppose that you're not given a reference node. Now, if you're given a reference node, if there's a ground symbol connected to a node, you use it. If not, and if you want to use node voltages, you can put the reference node anywhere you want. The reference node is just where you're defining the negative sign of the node voltages. For example, I can take a ground node, I can put it on the circuit. Let's suppose I don't have any ground node defined, and I want to use node voltages for some reason. I can just put a ground node in. I might strategically pick the location to make analysis easier, but let's just put it in the upper right. So that means that this upper right node is now the reference node against which all the rest of the voltages are defined. So this upper left node, which was V1, I'm going to call that V1 prime. It's no longer V1. V1 prime is indicating the voltage, the node voltage at this upper left node, but now it is the voltage between this upper left node and the upper right node, because the negative sign always goes at the reference node for node voltages. The positive sign goes at the node for which the node voltage is defined. Right? If I call this center node V2 prime, that applies to that whole node, then V2 is this voltage, right? Negative goes at the ground node, positive goes at the middle node there. And that leaves, I'm going to call the bottom V3. That was the ground node, but I'm left with that node to define V3. So that's V3 prime, I should say prime. So V3 prime has its negative sign at ground, its positive sign at this bottom node here. These voltages, so comparing left to right, V1, V2, V3, and V1 prime, V2 prime, V3 prime, they're measured between different points of the circuit. Look at where the polarities are. The polarity signs are. They're just different points in the circuit. So V1 is not V1 prime, V2 is not V2 prime. These are not equal. They're just different points in the circuit. Okay. I mean, you could maybe numerically one could work out to be equal if you design the right circuit, but in general, you're picking different points in the circuit to define these voltages. Okay. So a couple points. When I added the reference node to the circuit, either one, I didn't actually change the circuit. If I'm only adding one ground node, one reference node, defining one of the nodes as the reference, and I'm only defining one node like that. We'll talk about multiple ground symbols later, but if I only add one, I'm not changing the circuit. I'm just saying this is where I put the negative terminal of a voltmeter when I measure node voltages, and when I define node voltages, okay? So when I add a ground, it doesn't change anything. It only indicates a reference node for measuring or defining voltages. And then changing the reference node, like I did here from left to right, changing the reference node does not actually change any voltages across the circuit elements. It only changes the reference point for measuring node voltages. So in the left and the right circuit, if I have the current source, same values, and all the resistors are the same values, then even though I've moved the reference node, and V1 is not V1 prime, V2 is not V2 prime, whatever, if I were to take a voltmeter and measure across each one of these individual resistors on the left and on the right, you'd have the same voltages across each resistor. You have the same currents through each resistor. I'm not actually changing the circuit when I add or move a ground symbol, a single ground symbol in a circuit. What I am doing for node voltages is I'm moving the negative side of all the node voltage where they're defined. So let's see. Someone asks in the chat, are voltages continuous across nodes even with circuit elements in parallel? So if circuit elements are in parallel, those two circuit elements, if you have two circuit elements in parallel, have the same voltage across those. KVL still works, right? KVL still works throughout the circuit. Circuit elements in parallel have the same voltage across them. So I think that's what you're asking. If not, then you might either type some more or stop by office hours. We can draw out your specific question on the whiteboard. Okay. All right. One important thing about node voltages is this, that once you've used node voltage analysis, which we will get to calculate all the node voltages in a circuit, once you have all the node voltages solved for, you are only one or two steps away from solving for all the other circuit variables, all the other currents, all the other powers in the circuit. Okay, so that's what's nice about having a methodical way of solving for node voltages, is then you can go one more step and calculate currents, calculate powers. It's really easy from there. Let me show you that, and at the same time, I'm going to show you a process you're going to be using for node voltage analysis once we get there. Here's the circuit that we were just working with. I've defined two node voltages and resistor R1. Okay. Let's suppose I want to relate Vx and Ix to the node voltages V1 and V2, and this will help us later. Let me isolate this part of the circuit. Okay, so I'm going to isolate this and just kind of break it out over here so we can just concentrate. It's still in the circuit, but I'm just concentrating on it here. So I've defined Vx like this, Ix like this. And if I were to explicitly draw the polarities of V1 and V2, these would be those polarities with V1 and V2. To solve for Vx, I could write a KVL equation, minus V1 plus Vx plus V2 equals 0. And you would see the relationship between Vx and the adjacent node voltages is Vx equals V1 minus V2. All right. If I wanted to solve for Ix, well, by Ohm's law, Ix is Vx over R1. And I can relate Vx to V1 and V2. So I get this. Ix is V1 minus V2 over R1. Here's what I want you to take away from this. If you want to know the current that is going in the direction of Ix from V1 to V2, if I may call this node V1, this node V2, if I want the current going from V1 to V2 through R1, it's V1 minus V2 over R1. What if I define Vy with the opposite polarity and I want to calculate Iy going the opposite direction? Remember, Iy is just negative Ix, right? I can have arrows pointing in the opposite direction. Iy is negative Ix. Well, if I break that portion of the circuit out again, and I define Vy and Iy, okay, I can explicitly draw the polarities on this circuit, V1 and V2. By KVL, I can solve for Vy minus V1 minus Vy plus V2 equals 0. Okay, Vy is V2 minus V1. Okay, by Ohm's law, if I want to solve for Iy, Vy over R1 is Iy. I plug in the relationship between Vy and V1 and V2, and I get this. Okay, so I get the current going from V2 to V1. I'm labeling those nodes V2 and V1. The current going from V2 to V1, which is IY, is V2 minus V1 over R1. Now, IX is negative IY, so these equations should make sense. But this shows you a couple things. When we get to node voltage analysis, you're going to have to use terms that are current terms in a KCL equation. So we'll get to that. But also this shows once you have the node voltages, you're one step away from calculating currents through a resistor. And you're also one step away from calculating power for a resistor once you have the node voltages. Okay. All right. So these are all the prerequisites for doing node voltage analysis. And we'll jump into the actual node voltage analysis process next time. So in closing, don't forget assignments are up on Canvas. Take a look at those due dates and due times. Take a look at when the lab 1 and pre-lab 2 are due. Those are all posted. One submission per team for all labs and pre-labs going forward. See the Slack workspace, post questions there if you have any questions. I will start office hours in just a few seconds. So if you would like to chat, then stick around. If not, I'll see you next time. Have a great night.